Hi there, yeah. Unfortunately, the abstract for this was a little speculative on future development happening between the abstract being submitted and now. Unfortunately, that development has not exactly happened. So part of this will be a call for more interest from you guys. And also, this is a good segue following Daniel's talk, because a lot of the outstanding work is in relation to multi-master and multi-robot environments. So to start off, I'm going to talk about what is going on with tf2, what's there, and what's going forward. A quick definition of what tf2 is simply, it's a refinement of tf. I wrote tf almost 5+ years ago. A lot of people have used it all around the world, and from looking at it and helping people use it, I realized there was a lot of shortcomings in the ways it was done. But it's also been proven to be very strong. So we wanted to come back and just take another pass at it and clean up some of the things that we could have done better, but keeping everything as similar as possible to make sure that people can migrate it forward. One of the biggest things we wanted to clean up dependencies. We've done a templated API. I'll come back and show you a little bit more details about that, but it means the core library doesn't have dependencies on all the linear math libraries available in ROS. We also have now first-class support for Python. The previous version had a wrapped version of the C++ available in Python, and the way we wrapped it meant that there were some ugly things that you could run into corner cases that you just couldn't work around. We also discovered that subscribing to /tf on anything but the simplest robot is like subscribing to a fire hose, and it can take up to 5% of your CPU just to subscribe to tf. Even on the PR2, and if you have 20 little scripts running in the background monitoring TF, that's all of a sudden a whole core. And related to that, we also identified that static transforms were something that could be treated as a unique case that could be treated differently and have significant improvements. So as I mentioned, we did the templated transform data method. We've got templated conversion methods, which allows you to easily convert from one data type to another. So if someone gives you a bullet vector and you want an eigenvector, there's now just a method to convert those. And TF will actually let you work with both data types at the same time. We've also separated out the ROS API from the non-ROS stuff. So the core tf2 library, it only needs the the messages. It does not need any other dependencies. And we also set up a remote-based query API. I'll come back to the static. And one other thing that we've done is drop support for the tf prefix. Any of you have done multi-robot stuff, you've probably used tf prefix. But it turns out that only about like 10% of this code out there implements tf prefix correctly if it implements it. And having something that's partially there and too complicated for most developers is actually worse than just not having it. So to give you a little bit of explanation about the data conversions, this is just a little bit of sample code here. You can see we're pulling in the bullet data types, the geometry messages, and the KDL. So if you allocate a bullet vector, and you can simply just call convert, and you go from the bullet to the message. And that's all you need to do. Because somebody like me has gone through previously and written the convert method that knows how to convert a bullet message to a bullet data type to the message data type. And likewise, if you've already done that, you can also just trivially go to a KDL vector, as long as the to-message from-message transforms are there. And it's even smart enough that the template logic will work, that if you want to go from a bullet type, you can see the bullet type and the KDL type don't necessarily have a direct conversion, but the compiler is smart enough to convert it to the message and then convert from the message to the KDL data type afterwards. And the neat thing with this is we've now got this new templated transform API, so you can see that you can transform any data type here. This is the generic API. It looks like the regular TF interface. And all you have to do is define a do transform for your data type. So if you want to convert any custom data type, you just define do transform of T, and then TF can handle it, which is how we break the dependency cycle where TF needs to know your data type. You just have to have this in your header. You'll also note that we added a return by reference, which will allow you to chain things nicely. So you can write in the existing TF, you have to pre-allocate something and then call the transform, and then you can use it in another line. You can now chain them in one line. And the cool thing about this is you can actually ask TF to transform things from one data type to another. You used to have to convert everything into the bullet data type so that TF could handle it. Now you can actually ask it to transform a bullet vector. You give it a bullet vector and say, transform it into a KDL vector that I want out using these parameters. Very powerful, and makes your code much simpler. So as I mentioned, we have the concept of static transforms, which are simply, the implementation is done is they're published on a latch topic /tf static. And this means that each publisher publishes things once, and anytime a new subscriber connects, you get all the things from all the publishers already. This means that all data that's on this topic will go once to each subscriber, and only once. And they'll just know that it's there, and if there's an update to it, it'll get republished to them. But static transform should not be changing. And there's also underneath, TF keeps the time history of all transforms. And with the static transforms, we simply say, well, it's static. There's no need to keep a time history. Anytime you query the transform that's published as static, it will return exactly the value that was last published and not bother to go through the linked list and incur the overhead of doing a lookup. Another improvement in TF, as I mentioned, that subscribing to /TF is like a fire hose. It has a lot of overhead. And it turns out one of the standard models in ROS is that you have a monitoring, usually like a Python script in the background monitoring, say, am I near the table? And the way you answer the question, am I near the table, you do a lookup from you to the table, but you may only need to care about this once a second. And if you want to ask us something like this once a second, you have to subscribe to the whole TF stream. Whereas we've just simply put in an action interface that says you can do this query you can submit a query via an action interface to a remote process, and it will give you back exactly the same interface in your code. And you don't have to subscribe to the full TF stream. So you're trading off overhead for latency, because if you're querying over action-based interface, it's obviously going to be slower than a local query. And this is also really useful if you, say, have lots of robots, and they're running over wireless with a limited link. So a couple of TF2 has actually been around for a couple of years. It's currently in experimental mode. It's very close to be done. There's lots of people already using it. I haven't released it as a full release because I want to finish some of the outstanding issues that I'll get to later. But as an example of people using TF2 is PR2 plugs has been converted to use TF2 inside of it. We went through the process of doing this, and we made sure we verified correctness and robustness. Many of you have probably seen PR2 plugs running. It plugs in, and you don't think about it, and we're quite confident that TF2 is mathematically correct because of this. Another example of taking advantage of TF2 is the robot web tools, recently announced out of Willow Garage and a bunch of collaborators is a push to make ROS tools available on websites. And it turns out that subscribing to TF on your browser is also not a good idea. And so what they put together is a tool that will take the TF tree, subscribe to it, build it in local memory, and then republish it periodically or on demand as you set the parameters as an entire tree to your web browser so that you can use it. You get a whole TF tree in your web browser, but it's much simplified, and the browser can have much lower bandwidth requirements. So that's the state of TF. I want to now look a little bit forward. One of the major things that Daniel brought up earlier is you start dealing with multi-robot cases, and you got partition networks, and having a fire hose of one TF going between multiple robots suddenly becomes impossible when you start thinking about going over wireless. Likewise, there's a major issue with disambiguating similar robots. If you have two robots and they both have the head frame, all of a sudden they can't actually share data effectively. So when you're talking about sharing TF data, there's a lot of things to think about. What are the frames you're interested? How often you want updates? How much lag can you tolerate? How much error can you tolerate? But also how much bandwidth is okay. And you have to think about all these things. And we need to put together an API so you can set these tolerances for whatever your application is and make TF data available remotely via that. And as I mentioned, going deeper into the multi-robot case, so say you have two robots like this, Robot 1 and Robot 2. They look very similar. They probably have the same software running underneath. And they also have all the same frame IDs. So just looking at very simple, each one has a TF topic and a scan topic. They're publishing a base scan in the base link. And you need to get all the data from, like Robot 1 and Robot 2 want to be able to share their data, but it turns out that they're both publishing the base link in their scan, and if you want to just take data from one robot and put it on the other one, you're going to have a major problem because they're both going to say, well, this scan is from base link, and if they're looking opposite directions, the two scans are going to be mapped on top of each other because they're referencing now the wrong coordinate frame. So you need to be able to do something like take base link and turn it into Robot 1 base link. And that's relatively easy to do for the TF topic. It's a nice tree. You just take everything on Robot 1, prefix Robot 1, and send it on to Robot 2 as TF topic. However, the data is not that obvious. In the case of a laser scan, it's relatively straightforward. You just simply do a search and replace any frame ID, replace it with the prefix frame ID that you want on the other end. But there are cases where this doesn't actually work if you have embedded frame IDs inside of the middle of a payload, which are, they may not actually want to get referenced. If it's saying what is the parameter for my settings, what is such as a cost map parameter or something like that. So the big things outstanding are how to deal with these multi-robot, multi-master cases, and I'd like to resolve that before recommending the entire community switch over to TF2. So, questions?